Hello, and welcome to our final year project. My name is Jay Ramler, and along with my other group members, Mauz Asghar, Jack Lee, and Samson Zeremariam, we will be presenting our topic of a conceptual design of a water distribution system for the Village of Meath Park. To start things off, I will cover a little bit of the background behind this project. When deciding what we were going to do, the group felt that we wanted something hands-on and that we could actually put together. Majority of the classes that we took during our study were related and more focused on fluid dynamics. This gave us a relative idea as to the general category of topics that we would look at. It wasn't until UniV 400 that we were emailed a list of possible project ideas that we could use. One of these ideas was to design a water distribution system for a small town in Saskatchewan. The group felt that this topic checked off a lot of the boxes that we were looking for in our project. In the past, we've had lab sessions in which we've learned to use a software called EPANet. This program can be used to model water distribution systems, is free to use, and can be easily accessed at the university. Now knowing what we were going to do, the only question left was to figure out where this design would be implemented. Samson had gotten in contact with the Saskatchewan Water Security Agency, which provided us a list of places that were in need of a new system. After doing a little bit of research on our own of the proposed places, the group chose Meath Park, as it is small enough that we could design for the entire village and that the original system had not been updated since it was built in the 1960s. This village also had its contact information on their website and was easy to get in contact with.
The problem has arisen in the village of Meath Park in the late 21st century, which was caused by the water distribution system shown in figures 1 and 2. By the information provided by the Water Security Agency and the newsletters from Meath Park, our group identifies it was caused by the aging in metal pipes. When the pipe is being old, they cause corrosion. Then the pipe lost its own strength and being fatigued, causing cracks in pipes. Additionally, it will reduce bond strength, reduce shear capacity, and limited ductility. Overall, all of those problems will increase maintenance costs, and it may charge more money than replacing it to new ones. In this slide, it confirmed that the pipe is being old and rusty. According to the document provided by the Saskatchewan Ministry of Environment, the pipe should be painted or replaced due to aging. Once again, this proves that the condition of pipe is unpleasant and may have a potential impact on the residents' health and safety later on. In the next slide, we're going to discuss what software we use and how we use this software to prepare and analyze our data. Also, we are going to discuss the theoretical analysis on economical, environmental, and social aspect of our project. The primary procedure to start this project was to take a satellite picture from Google Earth. This picture will then transfer to the software called AutoCAD. This software will allow us to sketch the main roads and house on top of the picture. Then the drawing will transfer to the software called EPANet. This software will determine the best and most efficient water distribution system design. It analyzed the total flow, quality of water, total pressure, and total head loss of the pipe, and these values are all critical factors to design a water distribution system. To operate the software, we need to insert values such as PhD, ADD, pipe diameter, pipe roughness, and elevation of the village. The PhD and ADD were 71 and 157 cubic meters per second, respectively, which were provided by the Water Security Agency. The smallest pipe diameter we can use was 150 millimeters to meet the City of Regina Development Standard Manual. We can assume that by using Bernoulli's equation, the pressure of the line will be smaller than the larger pipe, and the velocity of the water will increase, which is reasonable for a smaller city where the water demand is low. The pipe roughness of PVC pipe was 0.0010 millimeters provided by the engineering toolbox, and the elevation of the village was 482 to 483 meters. After inserting all these values into the software, we have to identify where the village was getting water from. The mayor of the village provided us the place of the reservoir in the picture at the top right hand side. This is the closer view of the map where they pump the groundwater supplies to the pipe. It placed on the railway avenue close to the Meath Park Rec Center. Then we designed 3 different water distribution systems to compare them economically, environmentally, and socially. The beginning of all 3 designing processes is similar. The reservoir and pumps are the starting point of the process, and the 2 pipes diverge into 2 different directions. For the branch system, the main pipes are placed under the main roads starting from the main pump. Then sub-main pipes are divided into branch line which are placed under the smaller roads to serve water to each house. This system is important to verify that the pipe is not connected to each other. For looped system, the system reaches the dead-end flow. The pipes need to be connected back to the main pipe to make it a loop system. It is recommended to place the pipe on the back alley so the pipes are not intruding on any residents' properties. For the combined system, the high-density commercial area, high-density residential area, and school area must be identified. The reason is that this area will get the loop system, so if there is the maintenance of the pipes are required, it can still serve the water to the residents. On the other hand, the low-density residential area will get the branches system, so we can save money on the project budget and also doesn't affect many residents.
It is our job as environmental engineers to produce a sustainable design which would benefit the Village of Meath Park in a positive way. To achieve this objective of a sustainable development of water resources, it is necessary to consider the aspects of design and management of physical infrastructures. The selected pipe material has a large impact on the sustainability of the design. This project proposes an index called In Situ Sustainability Index, or ISSI, which can be used for the pipeline's materials choice for drinking water systems and would take into account both technical and environmental aspects. This index considers the interaction between piping and laying soil through the in situ elasticity coefficient and the impacts of material used for water systems piping through the life cycle assessment. The pipe material has to be based on the cost-effectiveness ratio. So first, we look at the pipe's hydraulic behavior, which is the interaction between pipe and water in relation to the hydraulic operation of the network, and the static behavior of the pipes, which is the interaction between pipe and laying it in the soil in relation to the forces acting on the pipe soil system. The pipe static behavior characteristics in relation to the soil are defined depending on its rigidity and that its aptitude not to deform due to load. Stiffness is defined by the rigidity modulus depending on the material characteristics through its elastic modulus E and the size of the pipe through the inertial moments I and J. The first dependent on the tube thickness alone, the second from the ratio between the thickness and diameter of the pipe. Regarding the LCA application, its objective is to evaluate the impacts associated to the production phase of the different types of materials. A total of 10 test pipes of different materials are analyzed, chosen from the most popular ones on the market: steel, iron cast, grass, reinforced cement, concrete, unreinforced concrete, fiber cement, PVC, PPE, PRFV, and PE are considered.
Some of the social aspects that we looked at in this project include design period and population forecasting. Design period can be defined as how long the system was built to last for. For this project, we researched different design periods for other projects that were similar to ours and came up with a range of 22 to 30 years. It is important to know the design period when first designing a project so that if you have older equipment in use and cannot last as long as the intended period, you can replace it with new machinery that will. Population forecasting can be used to help identify the design period. It is used to predict whether the village will have any changes to the population over the course of the next few years. To understand if the village's population would grow or decline, we took a look at Stats Canada's website and analyzed the previous 10 years of data. What we noticed is that the population has been floating around 170 to 200 people. This meant that we don't need to build our system for a large expansion, nor would we need to change our system vastly, meaning that we could have a longer design period. The last thing that I want to mention before we move on to the results section of our presentation is how we made decisions for social impacts. We created a scoring system that you'll see later in the presentation that allows us to quantify how we felt about 6 important social issues that could arise in our project.
All 3 designs run a simulation successfully, which means all are able to distribute water to each home and building. As well, all systems maintain the maximum limit of 1.5 meters per second recommended for distribution systems. Pipe 25 had the largest flow in all 3 designs because it is the farthest from the water reservoir. Now, when we look at the looped system, we can see that it has lower fluid velocities than the branch system. And this reduces the head loss, which increases the capacity of the system. When you have a higher capacity, fire protection is increased for the system. When discussing the technical aspect of the 3 designs, the loop design is the most favorable. This also makes the branch system least favorable system because of its high fluid velocity. In the next page, we can see the combined system and its fluid velocity, head loss. By looking at the numbers, we can see that the combined system has a lower fluid velocity than the branched, but higher than the loop system, which in turn makes the combined system the second favorable option.
For our economical analysis, we decided to use a cost model instead of contacting different suppliers for the price of different elements of our project. We found this would be far more efficient as many different suppliers require capital beforehand before giving the estimate. As well, we found that the cost model would be far more accurate. We used a cost model derived from the Water Supply and Research Division of the U.S. Environmental Protection Agency. This cost model not only specialized for the cost of villages and small communities, but the cost model is very accurate and precise, and this is evident on the graph. The cost estimation for several projects using the cost model is on the y-axis, while the actual cost of the distribution systems are found on the x-axis. And as you guys can all see, the estimation and actual costs are nearly identical. The U.S. Environmental Protection Agency uses data from previous water distribution systems when deriving formulas to determine costs for different components of the project, such as excavation, trenching, and base installation. These formulas obviously differ depending on the material, soil, slope, and other variables, but generally they are similar. To determine the cost of a component, you simply plug in your independent values, which is your diameter and pipe length, into the formula, and then you receive the cost of that certain component. Now going on to the next slide, the costs that we determined were base installation, excavation and trenching, embedment, backfill and compaction, traffic control, hydrants, sheeting and shoring. The costs that we ignored were engineering costs, insurance costs, legal costs, utility interference, and pavement replacement costs. Most of these costs were ignored because Meath Park told us that these costs were costs we would not encounter while building a water distribution system for them. Our total costs are summarized in the following table, and the most costly component of the project was embedment, backfill, and compaction, and then surprisingly the least costly was traffic control. After calculating the cost, we had to adjust our total to account for inflation. The cost model was created in 1997, and there had been nearly a 51% increase in consumer price index since then. After accounting for inflation, the cost of our branch design was nearly $635,000. Our loop design had a price of $1.1 million, and our interactive combined design had a price of nearly $870,000. Obviously, the price of all these projects are relatively expensive when we consider the fact that this water distribution system is only meant for 179 individuals. But I will discuss at the end of this presentation why the government of Saskatchewan should be willing to pay this price.
In the ISEC figure to our left, we can see which pipes are less effective when considering hydraulic behavior. On the right, the LCA figure, which was done by a consulting company named Cogent Engineering, showcases each pipe and its impact. Now in the next slide, we can see the ISSI index, which creates a link between the ISEC and LCA analysis. With the same static hydraulic performance, The results show that the material with a higher ISSI value is less sustainable than another material with a lower ISSI. Since our design selected PVC for the pipe material, we can see our design is one of the best materials when considering sustainability, especially when cost is considered an important factor for such a small village like Meath Park. PVC is the most optimal choice for material for the pipes.
So now we're going to present the social impacts. As mentioned before in the methodology section, we took a look at 6 social impact questions that we wanted to put numbers to according to how we felt about each. These 6 questions are: will there be any changes in population size, age, or structure to the village? Will there be increasing demands on local facilities or services? Will the project create new jobs during construction or operation or cause the loss of jobs? Will the quality of living be better or worse? Will the project be economical to the village? And lastly, will the project create better safety measures such as fire suppression? After evaluating these, using the scoring chart shown on the slide, we summed up the total and came up with the following. The loop system scored a 5, branch system 7, and combination system 4. The lower the number, the more optimal the system would be socially for the village. As it turns out, our combination system is the most optimal, and this can be from a number of things. The combination system takes pros from both the other systems while limiting the amount of cons that it has. For example, fire safety is best in a loop system. The combination system shares similarities with the loop system in that it still has access to water in the event of a line break so that it can provide fire hydrants with water. For this reason, the 2 systems ended up with the same rating. Same thing goes for the quality of living. The combination system does have some zones where chlorine residual will not continue to mix, but because these zones are so few, it only affects a small portion of the village. The looped and branch systems have no middle ground. They are either the best options or the worst. This results in having areas of social impacts that are undesirable, where the combination system, although having some flaws, does not have any one area that it lacks in.
After comparing all of the results, it is time to choose the best design out of the 3. If we look at the table to our right, at the bottom, the final scores are shown. Final scores show that the combined system had the lowest average rank throughout the 4 categories. However, when taking into considerations the weights of each section that were determined by the group, the combined and loop system both tied for best system. The branch system finished second in the average rankings, but fell short in the categories that were weighted the most. This meant that the branch system finished last for the optimal system. Because the combined and loop system are tied with weighted ranking, the average rank is the deciding factor. With an average score of 7 and a weighted score of 1.95, the overall best design of a water distribution system for Meath Park would be the combination system.
For our project, we also conducted a thorough environmental impact assessment of our combined distribution system. First, we had to screen to determine what kind of impact assessment was required, and it was determined that a limited EIA would do. Our EIA investigated all the negative effects that the distribution system could cause, such as decrease in air quality, land disturbance, habitat loss for animals, and capital cost. We also analyzed the positive impacts, such as the increase in water quality, enhancement of human health, and job generation. We quantified all these effects and determined whether the project was deemed sustainable. I could go more in depth about our EIA, but due to limited time constraint, I will only go over our conclusion. At the end of the day, we believe that the positives that the project brought through an increase in water quality and the increase in human health substantially outweighed the negative effects. We believe that the health of rural individuals have been ignored for an extensive amount of time. Individuals living in rural areas such as Meath Park suffer tremendously from the health system at large, whether it be due to a lack of doctors or health infrastructures present near them, or the other million of reasons. We cannot add another stressor to the health quality of these individuals. The health of rural communities can no longer be ignored, and by implementing this water distribution system, we are no longer ignoring the problem, but finally beginning to address it.
With that, we would like to conclude our presentation by thanking Dr. Kelvin for supervising us and assisting us throughout the project. Also, we would like to thank Ben for his assistance with EPANET. And with this, thank you for listening to our presentation.